Somewhere over the open Pacific, thousands of miles from the nearest coastline, the ocean is doing something it should not be able to do this late in the season. The water beneath a patch of open sky near Guam has climbed past 30 degrees Celsius, and it keeps climbing, storing heat the way a battery stores charge, and on the morning of August the 20th, meteorologists watching satellite loops in real time saw a tropical depression spin into existence over that exact patch of ocean. Within hours it had a name. Within a day, forecasters were no longer asking whether it would strengthen, but how far, how fast, and how much of that strength would still be intact when it reached land. Its name is Saudal, and if the numbers now sitting inside the world's most advanced weather models are even half right, it will not be the last storm this year to force scientists to reach for words like unprecedented. Because here is the part almost nobody outside the meteorological community fully grasped until this year. 2026 was never supposed to be quiet. It has already produced a super typhoon that tore through the Mariana Islands with sustained winds estimated near 180 miles an hour. It has already produced a second Category 5 equivalent storm that struck the same battered islands only weeks later. It has already produced a third in the final days of July, so ferocious and so far west that forecasters called it the strongest tropical cyclone ever recorded so close to the international dateline. 3 Category 5 storms in one ocean basin before the season even reached its traditional peak. And now, in the final full week of August, a fourth contender is spinning to life, and the same atmospheric engine that built the other 3 is idling underneath it, fully fueled and waiting. To understand why this particular week matters, you have to go back to April, to a storm named Sinlaku, because everything happening right now traces back to what Sinlaku proved was possible. Sinlaku formed absurdly early in the season, off the coast of Chuuk, at a time of year when the Pacific is not supposed to be warm enough to build a monster. It didn't care. It intensified into the first typhoon of the year, then the first super typhoon, and by the time it reached its peak, the Joint Typhoon Warning Center clocked its sustained winds at 185 miles an hour, with a central pressure that plunged to 890 millibars. For scale, the pressure reading places Sinlaku among the most intense tropical cyclones ever measured on the planet at any time of year, in any ocean. It made landfall on Saipan as a weakened but still catastrophic system, killing 17 people and causing damage north of $450 million on islands that are home to barely more than 50,000 residents combined. Scientists studying the storm afterward kept returning to the same unsettling detail. Sinlaku formed in April. Historically, storms of that magnitude do not exist in April. The ocean simply isn't supposed to hold enough energy that early in the year to support a system like that. And yet it did. Meteorologists combing through the historical record afterward pointed out that Sinlaku was the strongest tropical cyclone to form anywhere in the northern hemisphere during the month of April since a storm called Surigay back in 2021. And Surigay itself had been treated at the time as a once-in-a-generation outlier. 2 once-in-a-generation outliers, 4 years apart, both arriving in a month the record books say shouldn't be capable of producing them, is the kind of coincidence that stops looking like a coincidence the more times it repeats. Then came Bavi, barely 3 months later, aimed at the exact same islands that were still clearing debris from Sinlaku's path. Bavi rapidly intensified to Category 5 equivalent strength, with the Joint Typhoon Warning Center reporting maximum sustained winds of 162 miles an hour and a central pressure of 919 millibars. Machine learning ensemble models run by DeepMind, the same artificial intelligence lab behind some of the most accurate storm forecasts now in existence, put 60% odds on Bavi's winds eventually topping 180 miles an hour. Forecasters pointed out, almost in passing, that Bavi had the potential to rival not just Sinlaku from earlier in the year, but Typhoon Mawar, the storm that hit Guam in 2023 and stood, until this year, as the most powerful system to strike the island since the year 2002. 2 storms, 1 island chain, both among the strongest ever observed at their respective points in the calendar. Local officials on Rota, a small island home to roughly 1,500 people, braced for what forecasters described as the worst conditions likely to hit anywhere in the Marianas. And then, less than 72 hours after a separate Category 5 hurricane spun up in the eastern Pacific, a storm named Genevieve, the western Pacific produced its third monster of the summer. Super Typhoon Dolphin reached Category 5 equivalent strength in the final days of July, and meteorologists tracking its formation pointed out something almost eerie about where it had built its strength. Dolphin developed so close to the international dateline that scientists studying its formation called it the strongest typhoon on record to intensify that far east in the basin. It threatened no immediate coastline when it peaked, which meant it never generated the kind of headlines a landfalling storm produces. But for the people whose job is to track the underlying engine driving these systems, Dolphin was arguably the most important data point of the summer. It confirmed a pattern. It wasn't one freak storm. It was a signature, repeating itself in different corners of the same ocean, month after month. And the timing of Dolphin's emergence, arriving within 3 days of a separate Category 5 hurricane peaking on the opposite side of the Pacific, told researchers something else worth sitting with. The ocean's capacity to build these storms right now isn't confined to one narrow stretch of longitude near a handful of vulnerable islands. It spans nearly the entire width of the world's largest ocean, from the eastern Pacific off Mexico and Central America to the far western edges near the international dateline, an almost continuous band of water primed to turn any organizing disturbance into a record book entry. The scale of that band is easy to state and hard to actually picture. The Pacific Ocean alone covers roughly a third of the planet's surface, and this year, functionally all of it, from one coastline to another, has spent months sitting warm enough and calm enough in the upper atmosphere to support explosive storm growth practically anywhere a disturbance happens to organize. That is not the normal state of affairs. In an average year, only isolated pockets of the basin carry that combination of heat and low shear at any given moment, which is part of why Category 5 storms historically have been rare enough that a single one dominates headlines for a week. This year, meteorologists have had to track 3 of them essentially back to back, and now a 4th, treating each new intensity forecast less as a shocking anomaly and more as the expected outcome of an ocean that has simply stopped behaving the way the historical record says it should. That signature has a name, and it is the reason every meteorologist quoted in this story keeps circling back to the same 3 words. El Niño is back. Not a garden variety, El Niño either. Forecasters, tracking sea surface temperatures across the equatorial Pacific, describe the current event as one with the potential to rank among the strongest ever measured. And when you combine that with what scientists call a positive Indian Ocean dipole, a separate but related pattern of warm water sloshing toward the western Indian Ocean, you get a rare kind of double engine, warm water stacks on top of warm water. Wind shear, the atmospheric force that normally tears weak storms apart before they can organize, drops to unusually low levels across huge stretches of the western Pacific. And into that gap, storm after storm has been free to do something meteorologists call rapid intensification, a technical term for a process that looks from the outside almost supernatural, a tropical depression that was barely a smudge on satellite imagery. 48 hours earlier, suddenly explodes into a Category 4 or 5 system, gaining 60, 80, sometimes over 100 miles an hour of wind speed in a period so short that evacuation planners are running out of lead time to react. This is the part scientists want people to sit with because it is not a one-season anomaly. Seasonal forecasters tracking the Northwest Pacific Basin this year projected an above-normal typhoon season from the very start of 2026, driven explicitly by the developing El Niño and that positive Indian Ocean dipole. Their estimate, published months before Sinlaku ever formed, called for 27 to 29 tropical storms or typhoons across the full year, a number meaningfully higher than the long-term average. By late May, 6 typhoons had already formed, roughly 3 more than the typical pace for that point in the calendar. Separate analysts, covering the insurance and reinsurance industry, the people whose entire job is quantifying catastrophic risk in dollars, went further, projecting that this typhoon season would rank among the most intense ever recorded for Asia, with 20 typhoons expected to form across the region, and 13 of them expected to reach intense, major hurricane equivalent strength. 13 in a single season, superimposed against a backdrop where the storms that do form are increasingly forming stronger, faster, and in places the historical record says they shouldn't, which brings the story back to Saudel, and to this week, because Saudel is not forming in a vacuum. It is forming inside the same overheated, low-shear environment that built Sinlaku, Bavi, and Dolphin, and the forecasters watching its development in real time are using language that should make anyone paying attention sit up. One widely followed independent meteorologist, tracking the system as it organized south of Guam, described it as forming over a huge expanse of untapped warm ocean water at extremely low latitude. The exact conditions, he noted, typical of an El Niño-fueled typhoon primed to rapidly intensify. His forecast, issued as the system was still just a tropical depression, warned that it looked poised to strengthen rapidly with little wind shear to slow it down, as deep in the tropics. Within roughly 48 hours, that depression had already become Tropical Storm Saudel, and the models that meteorologists trust most for extreme intensity forecasts, the same DeepMind ensemble that flagged Bavi's potential weeks in advance, were already showing high-end Category 4, potentially Category 5 strength, with central pressure estimates plunging into the 920 to 930 millibar range. For context, that range sits in the same neighborhood as Bavi's peak intensity from July, a storm that rivaled some of the most destructive typhoons to hit the region in over 2 decades. The projected path adds a layer of tension that the earlier storms didn't carry in quite the same way. Saudel's forecast track curves north-northwest before bending westward as it gains latitude, threading a path that several forecast models place uncomfortably close to the water south of Japan within the next 5 to 6 days. Japan has spent the back half of this decade absorbing an unusual number of intense typhoons, and a storm arriving at Category 4 or 5 strength, with a central pressure potentially bottoming out in the low 900s, would immediately rank among the most powerful systems to threaten the country in recent memory. Nothing about that outcome is locked in yet. Tropical cyclone tracks this far out carry real uncertainty, and small shifts in the steering pattern over the next several days could push Saudel toward open ocean, toward Taiwan, toward the Korean Peninsula, or toward a landfall scenario nobody has fully modeled. But the intensity forecast is the part meteorologists are treating as close to certain. The ocean heat is there, the low shear is there. The only open question is exactly how strong Saudel gets before it runs out of runway. And Saudel is only one piece of a genuinely global picture unfolding at the same moment. In the Central Pacific, a system named Lala has been grinding along well away from the Hawaiian Islands, but forecasters are already tracking a second storm forming southeast of Hawaii, expected to be named Moke, on a track that would carry it south of the island chain in the coming days. Two named systems, active in the Central Pacific simultaneously, is itself an unusual sight for late August. Meanwhile, in the Atlantic, the basin that has been almost eerily silent for most of this year, a shift is quietly building. The National Oceanic and Atmospheric Administration has spent the summer maintaining a below-normal forecast for Atlantic hurricane activity, citing conditions like unusually strong wind shear tied to that same El Niño pattern, along with drier-than-average air sitting across huge stretches of the basin, exactly the opposite of what fuels rapid intensification in the Pacific right now. Only 7 to 13 named storms are expected across the entire Atlantic season, with as few as 0 and no more than 2 reaching major hurricane strength. But even that quiet basin is showing signs of stirring. Forecasters have flagged a strong tropical wave expected to move off the coast of Africa within days, developing into what one meteorologist bluntly called the best chance yet, maybe of the entire year, for a tropical storm or hurricane to spin up in the main development region. Water temperatures across the wider basin remain unusually warm for the time of year, with parts of the Gulf sitting near 30 degrees Celsius, more than warm enough to support intensification if a system does manage to organize despite the shear working against it. Even the southern hemisphere basins, months away from their own traditional peak season, have already produced warning signs of their own. Far south of the equator, the southwest Indian Ocean saw a named storm form in early August, a timing unusual enough that forecasters noted it as the first August named storm in that basin in years, a small data point on its own, but one more thread in a global pattern where basins are behaving outside their historical calendars more often than the long-term record would predict. None of these individual anomalies proves anything in isolation. Weather is noisy, forecasts carry uncertainty, and any single storm forming a few weeks early or a few miles per hour stronger than expected can plausibly be dismissed as natural variability. What is harder to dismiss is watching 4 separate ocean basins, on 4 separate continents' doorsteps, all lean toward the same extreme end of their historical distributions within the same 8-month window. Step back far enough, the picture that emerges is one meteorologists rarely get to observe with this much clarity in a single calendar year. Multiple ocean basins, thousands of miles apart, are behaving as if they are all plugged into the same underlying power source. And in a sense, they are. The developing El Niño event is not a Pacific-only phenomenon. It reshapes global wind patterns, it redistributes ocean heat across entire hemispheres, and it recalibrates which basins get the fuel for monster storms and which basins get suppressed. This year, the Northwest Pacific drew the winning ticket, and it has cashed it in 4 times over, first with Senlaku in April, then Bavi in July, then Dolphin at the very end of July, and now Saudel in the final days of August, each one forming in a slightly different corner of the same overheated ocean. Each one, another data point in a pattern scientists have been warning about for years, but rarely get to watch play out with this much force compressed into a single season. The scientific community's concern here isn't really about any single storm. It's about the mechanism. Rapid intensification, the process by which a weak, disorganized system explodes into a major hurricane or typhoon in a matter of hours rather than days, has become measurably more common in recent decades. And the physical explanation researchers keep returning to is deceptively simple. Warmer ocean water holds more energy near the surface, and tropical cyclones are, at their core, heat engines that convert that stored ocean energy directly into wind speed. The warmer the fuel, the faster and more violently the engine can run, provided the atmosphere around it stays calm enough, low enough in wind shear, to let the storm's internal structure organize without being torn apart. This year, across the western Pacific, both of those ingredients have been present simultaneously and repeatedly, which is precisely why forecasters keep using words like unprecedented, why insurance analysts keep revising damage estimates upward, and why a storm that was a barely organized depression on a Tuesday can be flirting with Category 5 strength by the following weekend. To grasp why a handful of degrees of ocean warmth can produce a difference this dramatic, it helps to think about what a tropical cyclone actually is at a mechanical level. It is not simply wind moving in a circle. It is a machine built to pull heat out of the ocean and convert it into motion, drawing warm, moist air up from the sea surface, releasing that stored energy as the moisture condenses into towering thunderstorms wrapped around a central core, and then exhausting the spent air out the top of the system before drawing in more from below. Every part of that cycle runs faster and more efficiently the warmer the water underneath it is, right up until the storm reaches a theoretical ceiling. Scientists call its maximum potential intensity, a number calculated directly from sea surface temperature. When ocean heat content climbs, that ceiling climbs with it, and storms that once would have topped out at a strong Category 3 now have enough fuel underneath them to keep climbing toward Category 5, provided nothing else in the atmosphere intervenes to stop them. That is the second half of the equation researchers keep stressing, because heat alone does not guarantee a monster storm. Wind shear, the difference in wind speed and direction between the lower and upper atmosphere, acts like a hand physically tilting a spinning top. A developing tropical system needs to stack its thunderstorms directly on top of its own circulation to intensify efficiently, and strong shear knocks that structure sideways before it can consolidate, which is exactly why so many tropical waves fizzle out without ever becoming named storms at all. What made this Pacific season so combustible is that the same El Niño pattern supplying the record ocean heat has also been suppressing the wind shear that would normally keep that heat in check, removing the one variable that historically prevents every warm patch of ocean from spawning at Category 5. Strip away the shear, leave the heat in place, and the atmosphere effectively stops saying no. Researchers who study long-term storm records describe this as less of a single-season anomaly and more of a trend line that has been climbing for roughly 4 decades, even as the raw number of named storms forming worldwide each year has stayed relatively flat. Fewer storms overall, but a rising share of the ones that do form reaching major hurricane or super typhoon strength, and a rising share of those doing so through rapid intensification rather than the slower, multi-day buildup forecasters historically relied on. Sinlaku, Bavi, and Dolphin all fit that exact profile this year. None of them crawled toward peak strength over the better part of a week. Each one punched through multiple intensity categories in a window measured in hours, and Saudal's own forecast track, according to the intensity guidance meteorologists trust most for these situations, is already following the identical script. What makes this trend genuinely difficult for coastal communities to plan around is the shrinking window between warning and impact. A storm that intensifies gradually over 5 or 6 days gives emergency planners time to stage resources, issue evacuation orders, and move vulnerable populations to safety on a schedule that actually works. A storm that goes from tropical storm strength to major hurricane strength in under 48 hours compresses that entire planning window into something closer to a scramble. Officials on islands like Rota, population 1,500, or Saipan, still rebuilding infrastructure damaged by Sinlaku months earlier, are increasingly being asked to make life or death evacuation calls with less certainty and less lead time than the previous generation of storm forecasters ever had to contend with. And it isn't limited to small Pacific islands. Japan, South Korea, Taiwan, and the Philippines, nations with far larger populations and far more built infrastructures sitting in the path of these systems, are all bracing for a typhoon season that seasonal forecasters flagged as likely to be among the most intense on record before a single storm had even formed. Insurers and reinsurers, the industry whose entire business model depends on quantifying disaster risk years in advance, have been recalculating exposure across the region all summer. When analysts project that 13 of this year's typhoons will reach intense major hurricane equivalent strength, that number isn't an abstract meteorological curiosity. It is a direct input into how much it will cost to rebuild ports, seawalls, power grids, and housing stock across an entire region, and it shapes decisions being made right now about premiums, reserves, and which coastal developments even qualify for coverage going forward. Globally, the tally for 2026 already stands at 43 separate tropical systems, 23 of them strong enough to earn a name, with total damage, estimates north of $3.5 billion and confirmed fatalities exceeding 140, a running total that will almost certainly climb further before the year closes, and one that does not yet fully account for whatever Saudal, Moke, or the newly forming Atlantic wave ultimately produce. The human calculus on the ground looks very different from the spreadsheet version. On islands like Rota and Saipan, where entire communities are still repairing roofs and seawalls damaged by Sinlaku's April landfall, residents are being asked to evaluate a second or third major storm threat within the same calendar year, often before insurance claims from the previous one have even been settled. Emergency management officials across the region have started publicly acknowledging what meteorologists have been saying privately for a while. The traditional playbook, built around several days of advance notice before a storm reaches its peak strength, is increasingly unreliable when the storm in question can jump 2 full categories between one satellite pass and the next. Some coastal governments have begun shifting evacuation triggers earlier in a storm's life cycle specifically to compensate, ordering people to move based on a system's potential ceiling rather than waiting to confirm its actual peak, a strategy that trades the risk of an unnecessary evacuation against the far more dangerous alternative of running out of time entirely. There is a strange asymmetry sitting underneath all of this that the scientists tracking these systems keep returning to, almost as an aside, but it matters. The same El Niño pattern supercharging the Pacific is simultaneously suppressing the Atlantic, which means the United States, at least along its Gulf and East Coast beaches, has spent this year bracing for a season that, so far, has largely failed to materialize the way it usually does. Tropical storm. Arthur brought record rainfall to Louisiana back in June. Tropical storm Bertha followed in July without escalating into anything more serious. But NOAA's own forecasters, even while holding their below normal outlook steady through mid-August, keep pointing to the exact same warning sign now driving Saudal's explosive growth on the other side of the planet. Water temperatures across huge stretches of the Atlantic and the Gulf remain unusually warm for this point in the year, warm enough that if the wind shear currently protecting the basin relaxes even briefly, any system that manages to organize would have more than enough fuel waiting underneath it to intensify rapidly, the exact same mechanism currently reshaping the Pacific in real time. The tropical wave now approaching from West Africa is, in that sense, a test case. A relatively minor disturbance riding into a basin that has spent all year defying its own historical pattern, entering exactly the kind of warm, humid environment that, under slightly different shear conditions, has spun 3 separate storms into the most powerful category that exists anywhere on the planet. Scientists are careful, in nearly every interview and forecast note tied to this story, to draw a distinction between attributing any single storm to a single cause and describing the broader environment that makes storms like Saudal more likely to reach the extremes they are reaching. No meteorologist tracking the system is claiming that a warming planet personally built Typhoon Sidel in a laboratory. What they are documenting, storm by storm, season by season, is a shift in the odds, a loading of the dice that used to sit relatively evenly and now increasingly favors the high-end outcomes. The rapid intensifications, the 890 millibar pressure readings, the Category 5 equivalents forming in months, and in places the historical record says they shouldn't. That distinction matters because it is the difference between treating this week's forecast as an isolated curiosity and treating it as the latest entry in a ledger that keeps getting longer and heavier with each passing season. Nobody studying this data is claiming to know exactly how Saudal's story ends. Forecast models 5 and 6 days out still disagree meaningfully on where the storm ultimately tracks, and small shifts in the atmospheric steering pattern between now and the middle of next week could send it toward open ocean, toward a glancing pass south of Japan, or toward something considerably more direct. What forecasters are far more confident about is the intensity ceiling. The ocean heat sitting beneath Saudal's path right now is the same reservoir of stored energy that built Sinlaku into an 890 millibar monster in April, that built Bavi into a rival of Typhoon Mawar in July, and that built Dolphin into the strongest storm ever recorded, that close to the international dateline just weeks ago. There is no obvious reason, based on everything the models are currently showing, why Saudal would be denied access to that same fuel supply. Which means the honest answer, the one every meteorologist quoted across this story keeps circling back to, is that the strongest storm of the year so far might not hold that title for very long. And the ocean that keeps producing these systems shows no sign this week of running out of the heat required to build the next one. For now, satellites keep watching a spinning mass of clouds south of Guam tighten its structure hour by hour. Forecast models keep nudging their intensity numbers upward with each new run, and somewhere south of Japan, emergency planners are quietly beginning to run the same calculations that Guam, Saipan, and Rota have already run 3 times this year. Whether Saudal becomes the 4th chapter in that story, or whether the atmosphere shifts just enough to spare the coastlines currently in its projected path, is a question the next several days of data will answer. The ocean, for its part, is not waiting for permission.